The two that we just looked at were really just a review of last year's stoichiometry. This is the new stuff. This is the AP stuff incorporated. It's not that much more challenging, but we are now going to use the stoichiometry with solutions and with gases for ideal gas law experiments. All right, so you're going to explain changes in the amounts of reactants and products based on the balanced reaction of the chemical process, reaction there. Perform stoichiometric calculations combined with ideal gas law, calculations involving molarity, to quantitatively study gases and solutions. So this is a little bit step up, okay? Now here, solving stoichiometric problems for reactions and solutions. Identify the species presence in the combined solution and determine what reaction occurs. Because remember, if this is a precipitation reaction, not all chemical species are going to be participating. You're going to have some spectators here. So you kind of have to figure out what's spectating and what's reacting. So you need to make sure you have your balanced equation, of course, because we need the stoichiometric mole ratios. You need to calculate the moles. Like I said, going to moles is easier, and then determining limiting from there is easier. Calculate the moles of product and convert to grams or other units as needed, okay, as required. All right, so we have 10 milliliters of 0.3 molar sodium phosphate solution reacting with 20 milliliters of 0.2 molar lead to nitrate solution. Assume no volume change occurs. So basically, when you put them together, it's just additive. What precipitate will form? So the first thing really to do is write out our chemical reaction. So our first reactant here, sodium phosphate. We need to write the chemical formula. And what is the chemical formula for sodium phosphate? Think charges. What's sodium's charge? +1. What's phosphate? 3 minus. So this is going to be Na3PO4, right? Okay, this is a solution, so we know it's AQ. You don't necessarily have to write that in. Now, what is our other reactant here? Lead to nitrate. The lead 2 part tells me what about the lead? It's +2. And the nitrate we look up or know is -1. It's NO3 -1. So this is going to be PbNO3 with the 2 outside. All right, so we have our 2 reactants now. Which one is the sodium going to combine with? Nitrate, and we know sodium's +1, nitrate is -1, so that's easy enough. This is going to be NaNO3. Now, is that going to precipitate? No, because it has the alkali metal and it also has the nitrate. Both of them are always soluble. So this one stays aqueous. So now we look to our other product, which means the lead 2's combining with the phosphate. So we do Pb what? 3, PO4, 2. Now, thinking to our SNAP and our solubility rules, is that going to precipitate? Yes, phosphates are typically insoluble. It's not sodium, potassium, ammonium, or nitrate in the SNAP category. So this one we would label with the S. So this is the precipitate that will form. Okay? Wish I hadn't drawn that, but okay. I'll fix it. PV3, PO4. All right, so this is our precipitate that's forming. Now, what mass of precipitate will form? Before I can start approaching this, what do I need to do? Before I can do limiting and excess, I need to do what first? Balance. It's not balanced, so we definitely need to do that. What do I put here? 3. And what do I put here? 2, and that means this gets a, and this is an understood 1. You don't have to write the 1, but I'm just going to write it in there. Very good. We have that balance now. Now we can do the stoichiometry part. And this is where it gets fun, because now you have the added extra part of the molarity to contend with. But as we're doing in the solubility and solution notes, where we talked about molarity, we could use it as a conversion factor. So I'm going to move this over 1, 2, 3, like so. And I'm going to use my 0.3 molar as my conversion factor. Moles per 1 liter, and this is of my sodium phosphate, like so. Which product are we working to? We're working to the precipitate, right? It says what mass of the precipitate will form, so we got to work there. So moles Na3PO4, 2 moles of Pb3PO4, 2. So what is the mole ratio? This is a 2, this is a 1, right? 2 and a 1. Now technically we could go to grams here, but like I said, I like to stop at the mole. Take a look here. And might come in handy later. Second, wait. No, I don't want to grab. Okay. Let's see here. 0.01 times 0.3 divided by 2, right? So this ends up being 0.00150 moles Pb3PO42. Now let's look at the other reactants here. Do the same thing. Got to figure out what's limiting, because they gave us both information about both of our reactants. So yes, they become longer problems if they give us information about both reactants. This is the lead 2 nitrate. We work that one over. So moles of PbNO3, 2 moles of the Pb phosphate, the lead phosphate. Now we look at our balanced reaction. This one is 3 to the 1, like so. How many moles do we get here? 0.02 times 0.2 divided by 3. This one gives us 0.00133 moles Pb3PO42. Now, that was going to rewrite. Which one is our theoretical in moles? Which one? Which one? Top or bottom? The bottom, okay? This one is our theoretical. Okay, so this is the one we need to change over into grams to get the precipitate. And 1 mole of the Pb3PO42 gives us how many grams? I want to say it's like in the 800s because lead is massive. So let's multiply that by 3. 0.97 times 2 plus 8 times 16 for the oxygen. So I'm getting 811.54 grams. Pretty heavy stuff. We multiply that out and we end up with 1.08 grams 3PO4 2. So now this is where it gets a little dicey with the solution stuff. Because which ones are our spectators? Yes, sodium and nitrate are spectating. Oops, that's a minus. I know that because they're not in the solid, right? If they were in the solid, they would be reacting, but these two are not, so these are our spectators. That's another thing we should be paying attention to, okay? And if we're looking here then at our reaction, okay, this one came out larger, so this is our excess, and this one is our limiting, right? We can agree on that so far? But really, technically, the excess ion is only the phosphate, because the sodium doesn't do anything. So the one in excess is the phosphate. And the one that's limiting everything happens to be the lead ion. The lead ion is running out first. We have a little bit of extra phosphate, and then we have our two spectators that aren't doing anything. Can we agree upon that? Does that make sense? Okay, so you kind of have to mentally think about that as you're doing the solution precipitation reactions, because know that two of the ions aren't participating at all. The other two are participating, and therefore are going to be the ones where we're looking at limiting and excess. All right, so we got those. That's good. Now, they could ask you a question like this. What is the concentration of the nitrate ions left in solution after the reaction is complete? So here comes more of that solution stuff. Concentration of nitrate. Right? Well, is nitrate reacting? Nitrate is not reacting. So the amount of moles that we start with for nitrate will be the same amount of moles that's in there after the reaction, right? Okay, so we need to figure out the moles of the nitrate in there. And then the last step is to do what? Divide by the new volume. Yes, we are combining 10 milliliters of one with 20 milliliters of another. That means we're going to have a new volume. Right? Okay. So I take the reactant that has my nitrate in it, and that's going to be this one. Okay? We figure out the moles of the nitrate. 1 liter. This is the PbNO32, right? But in 1 mole of my lead nitrate here, how many nitrate ions get dumped into solution? 2 moles of nitrate, right? There's 2 of them in the formula, so we have to double that. So 0.02 times 0.2 times 2, I think that gives us what? 0.008. I think so. Check my decimal math on that. Yes, no, yes, no. Okay, good. So this is the moles of the nitrate. And we know none of it reacts, so that's going to be the total moles after as well. And our new volume, remember we have 10 milliliters plus the 20 milliliters, so that's going to give us 30 milliliters total. And we can just move this over, right? Change it to liters. So we divide this by the liters, and we get our concentration. So 0.008 divided by our 0.03. And what do we get here? 0.267 molar of nitrate. That's the easy part because that's the spectator, the one that's not reacting. Now we have to figure out how much is left of our one that is the excess, okay, that is left over. And you'll notice there's lots of space there for the next one, because lots of ways to do this. Question?
For this one, do we have to follow significant digits for like, alright, never mind. Because if you did it, never mind.
They all have 3, so I'm going with 3. So you don't have to write out all the zeros, but like up there they all have 3, so I go with 3 at the end. Yay, okay, we got it right. Now for the concentration of the phosphate ions. Because we already determined that lead runs out, but we have extra of the phosphate. Okay? So this is where you can do either method, and I'll show you both. But if you're doing the subtracting the product method, you want to make sure that you go back to these numbers, right? Start there. So that would be starting with those numbers. So we have 0.1. Okay. We start with our product amounts. And this gives us like 1.70 times 10 to the minus 4. This is moles, though, of the PB3PO4. Okay, so we have the difference of our 2 product moles. What do we do next? What do we work it to? We want concentration, so we need, we're going to need moles of our phosphate over the liters of the solution, right? If we're trying to figure out the concentration of our phosphate. So we need to take this and work it to what? We need to work it direct, look at me writing them backwards. This is 4, this is 3. We need to go to moles of just the phosphate. So we have 1.70 times 10 to the minus 4 moles PB3PO4 2. So 1 mole of this gives us how many moles of phosphate? 2 moles of our phosphate. Not lead, phosphate. There we go. So that gives us 3.40 times 10 to the minus 4, right? Moles. Then what do we need to do? Figure out the we need the liters. So, U volume again was what? 30 milliliters. We already determined that. So we just change that over to liters. And we can do the division. So divide by our 0.03. And we get our resulting concentration. I think that's the easy way, but we can try the limiting reactant way if you'd like to look at it. The subtracting of the moles is helpful because then all we have is like a one-step T-chart to get to moles of phosphate, right? So there's one way. Now, come on. All right. Method 2. If we want to do it the limiting reactant way, which reactant was the limiting one? The one with the lead in it, right? Okay. So this is the one that we would have to work to the moles of the phosphate. So, and you're going to see this one takes a little bit longer to do. Now, we work it to the excess just like before, same idea, you're working to excess. So, moles PbNO3 2 to moles of the Na3PO4. Okay? What was the mole ratio between these guys? One of them was a 2 and one of them was a 3. Lead was a 3 and the sodium was a 2? Okay. And 1 mole Na3PO4 equals 1 mole of the phosphate. All right, so this is going to give us the amount of moles consumed in the reaction. When you do limiting to the excess, it gives you the amount consumed. And we end up consuming 0.00267 moles. Okay? This is used in the reaction of our phosphate. Now we have to figure out how many moles of the phosphate did we start with. That's why the subtraction way of doing the product subtraction is probably easier in this case. So, how many moles did we start with? Got to work another track here. One mole Na3PO4 to 1 mole PO4. So 0.00300 moles. This is the starting amount of the moles. Then you subtract, right? Starting amount. Oh, I need another 0. Minus the used amount. That's going to give us what's left in there. This is what? 3.3 times 10 to the minus 4 moles. We still aren't done yet though, because we have to divide by the new volume. And the new volume and here we get 0.0110 molar phosphate. So as you can see, this number is very close to the other number we did. But if you do the limiting reactant way on solutions, it takes a lot longer. So subtract the moles first of the products and work it to the excess. It's much easier than doing this way, right? But you see, you can get the answer this way, it's going to take longer. I know. Everybody's brain's fried just about now? Okay. All right, well then let's switch gears. Yay! Okay, we got it right. Let's talk about gas law. Well, specifically the ideal gas law. When one collects a gas over water, there's water vapor mixed in with the gas. So you have your reaction here. So zinc is reacting with hydrochloric acid, and it's going to produce H2 gas. And you have it so the tubes connect it so that it goes in and is being collected over water. So as the gas fills this part of the chamber, it pushes the water down. Okay, and then, you know, we'll do this lab eventually, but you can measure, because we'll be using the graduated cylinders upside down, you'll be able to measure the volume of the gas in there that's being collected. So that's kind of fun. But because we're collecting it over water, and there's going to be a little bit of vapor pressure on top of the liquid, there's a little bit of water in there. So it's not all just hydrogen gas inside. Okay? So that's important here. The water vapor is mixed in with the gas, and we have to take that into account when we're doing the math. Okay, so basically you have to subtract the vapor pressure of the water from the total pressure in order to get just the pressure of the gas you're collecting. So as it's showing in this example, you have, in this case, they're decomposing the potassium perchlorate, and they're putting it in here and collecting the gas of oxygen inside here. What you do is you eventually line up your thing with the water level. You make sure that the gas line and the water line are equal, because then the pressure inside the container is going to be equal to atmospheric pressure. So then you take the reading of the atmospheric pressure, but that's still the total pressure of the gas plus the water vapor. So you do have to subtract out the vapor pressure of the water before you can use it in your PV equals nRT. So, key thing when you collect it over water, just make sure you subtract out the water vapor to get the gas pressure by itself without the water. Alright, so there is a problem in your problem set, and I put this in here for you because you need to be able to look up what the different water vapor pressures are at different temperatures, because they vary. And in the problem set, I don't think they just like provide you the table in the problem. But don't forget when you get to this problem that you're going to have to subtract out that water vapor pressure at whatever temperature it is. Okay? And you can Google these too. This is the one out of your textbook, but there are plenty of them, and they're in the different pressure units, because you have millimeters of mercury, you have torr, those are the same thing, but then you have ATMs, and you can have kilopascals and a couple other different pressure units. But just Google it. That might make it easier. All right, so ideal gas equation, PV equals nRT, of course, right? Where pressure is P, volume is V, but do remember that volume in this equation has to be in liters. Has to be in liters, and that's because all of the R's, the ideal gas constants, they are all in liters, okay? N for moles. Temperature T, but remember that's in Kelvin, so you have to add the 273 first, because we don't have any negative numbers in our gas laws. So absolute 0 is 0 K. There are no negative numbers. Add 273 to the Celsius before you plug and chug. All right, on your formula sheet, they also have this information I provided for you. It's a lot of information about the gases. So you don't have to memorize the R's. Here's the one for ATM. Here's the one for torr. And do remember, torr and millimeters of mercury are the same thing. One is just named after the guy, Torricelli, who invented the millimeters of mercury scale. They mean the same thing. All right, so now we're going to approach this problem of how to do stoichiometry with ideal gas law and collecting it over water. All right, so first things first, we need to write out the balanced equation for the decomposition reaction. And it tells us that hydrogen peroxide is decomposing into what? Water and oxygen. So let's do that. H2O2 decomposing into H2O and oxygen. So we need O2 for the oxygen. Now we need to balance it. So what do we need to do? We need to get rid of this oddball, right? Get rid of the odd here in the water. So put a 2 there. And then you put a 2 here. That cleans it up for you. So now we have 4 oxygens on both sides and 4 hydrogens on both sides. Now for the simple part. It says, what is the partial pressure of the oxygen gas? It says that the temperature and pressure conditions in the lab were 21.2 degrees Celsius and 761.4 torrs. So that's saying the atmospheric pressure in the lab was the 761.4. And you can look up the atmospheric pressure on your phone and it'll tell you what it is today. So talking about like pressure right now in our classroom. Oxygen gas is collected over water, a sample of water, at the 21.2 degrees. The vapor pressure of the water at that temperature, look how nicely they put it in the problem for us. So we didn't even have to look it up on the table. So here, how would we figure out the, this is the total pressure in the lab. This is vapor pressure of the water. How do we find oxygen? Subtract, it's very simple. Minus, because this is the water, okay, this is the total, and this is going to give us our O2. So subtract. This is the step that people forget to do though in the problem, and then their number is wrong. Okay? Like so. So far, so good, right? Not too bad. Just remember, subtract out that vapor pressure water.
Yes, sir.
What?
Okay, never mind. I was gonna ask what the state pieces of matter were.
Oh yes, of course. The hydrogen peroxide, because it says a sample containing it, that means it's a mixture. And I don't know if you know hydrogen peroxide, but it comes in a brown bottle at the pharmacy. It is definitely a liquid solution, and it's much better for cleaning out cuts than alcohol is because it doesn't sting as much. But it is a good cleaner of cuts and things like that. All right, now moving on. Assuming no deviation from the ideal part of the ideal gas law, how many moles of oxygen were produced? Any ideas what we should do here? PV equals nRT, I agree. Now, we just figured out the pressure of the gas. What was the pressure of the gas? 742.5 torr. Does it tell us anything about the volume of the gas that was collected? Yes, they gave it to us in what though? So we have to move it over 1, 2, 3 and change that to liters before we plug it in. Because remember, because of the R value, everything has to be in liters. Now we're missing the moles, so we're going to leave N the way it is. But if we look at which one do we want? Do we want the 0.08206 or do we want the 62.36 number for our R? Yes, we want the 62.36 because that's in torr times liters over moles times K. Now you don't have to write all the units in there, but I'm just writing them in there so you can see how they cancel. Now, what's the last thing we have to do for our T? Convert to Kelvin. So 21.2 plus 273. This is going to be 294.2 K. Now, if you watch me here, I'll show you how they cancel. K's cancel with K. The torrs cancel with the torrs. The liters cancel with the liters. So after we divide, the mole flips over onto the top, and we end up with our mole here, okay? So now all you have to do is plug it into the calculator and divide by the other side. So for n, I'm getting 0.00716. Did I get that right? Did I punch something wrong? Did you get that? No, I did punch something wrong. 42.5. I did 45.5.
We can just go directly from plugging in our numbers to n, right? So we don't have to go to the in between?
No, you do not have to show the work in between. So I'm getting 0.07132, right? 4 digits. When you change it to Kelvin, now it has 4 digits, and our pressure has 4, so our volume has 5, so we're going to keep 4. So that's moles of the O2. This is where the stoichiometry piece comes in. What was the mass of the hydrogen peroxide that reacted? Because now we know the moles of the oxygen, guess what we can find? So we do 0.007132 moles O2. Moles O2 to moles of H2O2. And what was it? This was 1 and this was 2 in the balanced reaction, I believe. Moles H2O2, and we need the grams of H2O2. And this, let me calculate that real quick, is going to be 34.02. And they love to ask this type of question on the AP exam. .4853 grams. All right, almost done.
I don't think we have time.
Well, we're almost done, so I'm just going to set it up for you. This last one, all you have to do is, what was the total sample amount? 8.15. Take your sample of your H2O2, divide it by the total, times 100, and you'll get your percent. That was in there, right? And that's about 6%. It's actually 5.95%. Yay! And I made it just under the bell. All right.